Hi, everybody. Today we have Helen Sirosi giving a talk on exploring ice sheet dynamics in the era of remote sensing technology. And we're thrilled to have her. She's at Dartmouth College in the Thayer School of Engineering. Her research interests are focused on better understanding and explaining ongoing changes in the ice sheets, as well as reducing uncertainties in the ice sheet contribution to sea level rise by combining numerical models with remote sensing and in situ observations. She earned her PhD in mechanical engineering from École Centrale Paris in 2011, was at JPL from 2008 to 2020, I believe. 2021. First as a visiting independent advisor, then NPP postdoc, then a scientist in the Sea Level and Ice Group all the way to 2021, where she co-founded and developed the ice sheet and sea level system model. She's a recipient of the NASA Early Career Public Achievement Medal and the AGU Cryosphere Early Career Award. She's a member of the scientific committee of the ice sheet model intercomparison for CMIP6, which is called ISMIP6. Please join me in welcoming her to our distinguished climate lecture series, and we can give her a round of applause.
Thank you, Eric, for the kind words and the nice introduction. Thanks for inviting me to join you today. Actually, as Eric said, I left JPL in the summer 21, but with COVID, I realized it's been exactly 4 years since I was here, so really, really nice to be back and see everyone. I thought I should talk today about exploring ice dynamics and thinking about remote sensing technology, since this is JPL. And then I realized I was a modeler, so I had to add this little subtitle. So that's really a modeler's perspective on how we can use remote sensing technology to think about ice sheets and how they are changing. And I'm going to talk about both Antarctica and Greenland first. But before we get started, here is a movie, actually a compilation of images taken one per day in front of Jakobshavn Isbrae, the largest and fastest glacier in Greenland. And the idea here is that we're seeing the front of the glacier here changing over time. We see calving events and big icebergs in the fjord. And we also see the ice flowing from the interior of the ice sheet towards us. And so when we talk about modeling of ice sheets, modeling of ice dynamics, that's what we're doing. We're modeling the flow of the ice here, flowing all the way from the interior of the ice sheet towards us. And so that's what I'm going to talk about. I thought that was illustrating nicely what I mean by that. And for the anecdote, Jakobshavn Isbrae is thought to have created the iceberg that sank the Titanic, an important glacier. But first of all, why do we care about ice sheets and why do we want to model them and understand them? If we look at the cryosphere in general, as explained in the last IPCC, cryosphere has a large potential to increase sea level rise over the next century. If all the mountain glaciers were to melt, it would raise sea level globally by about 40 centimeters. That's not much, but still something important. If we look at the Greenland ice sheet, and there's no map on this in this room, but the Greenland ice sheet, if you look at the map, looks like that. This is actually distorted because of the Mercator projections that we use in most of our maps, and so Greenland actually looks like that, so not that big. But still, it contains enough ice to raise sea level by more than 7 meters if all the ice were to melt. Antarctica is even bigger, 7 times bigger than Greenland, and it has enough ice to raise sea level by 58 meters if all of the ice were to melt. And so it has a large potential to impact sea level. But it's not just potential. It has already contributed significantly to sea level rise. If you look at the past, again, from looking at the IPCC numbers in the IPCC reports, if we look at the 2006 to 2018 periods, half of the sea level increase has been coming from melting of glaciers, Antarctica and Greenland. So it's already more than half of the sea level increase coming from the cryosphere. The rest comes from thermal expansion of the ocean and changes in land water storage, rivers, lakes, and reservoirs. So it's not just a potential contribution as we have here, it's already happening. What do we know about these changes? Well, I know you're all familiar with these movies, but we have now have a number of remote sensing observations for a long period. And for example, GRACE and GRACE follow-on provide a great picture of how and when and where the ice is lost in Greenland. And so this shows the mass loss of the Greenland ice sheet. So we have some nice time series here with a monthly value, so really nice spatial temporal signal. And then on the left, we can see where this mass loss is coming from. And we see that the changes are happening along the coast and propagating inland. And that created up to 5 meters of water equivalent mass loss in certain regions along the coast of Greenland. If we look at Antarctica, we see similar things, mass loss, about 150 gigatons per year on average. Unlike Greenland, we don't have a nice and neat seasonal signal anymore. We have more variability on different scales, a lot of interannual variability. And we also see if we look at where these changes are happening here, so in gray here we have the floating ice shelf, so not directly contributing to sea level rise. We see that we have even more variability than what we have in Greenland, with many regions losing mass, and including the Antarctic Peninsula here, the Amundsen Sea region here, the largest one. And we also have regions that are gaining some mass, for example, here along this coast, or ice streams fitting into the Ross ice shelf. And so we have really contrasting things happening in different regions in Antarctica. Now, so that's great. We have a lot of information about what happened the past few decades and what's going to happen in the future. Again, going back to the IPCC, here is a figure showing the global mean sea level change relative to 1900. And so we have the historical period here, and then projections until 2100 here in the future. And we see that, well, of course, carbon emission scenarios matter, and so we have different so we have different carbon emission scenario. And we also have some uncertainty around these scenarios, and most of this uncertainty comes from ice sheets. How are the Antarctica and Greenland ice sheets going to respond to these increased emissions? We also have this curve here, dotted line, low likelihood, high impact storyline, including ice sheet instability. What's this? This is processes we don't really understand. We don't really know how to constrain. That could impact the Antarctic ice sheet mostly, and could create much larger sea level contribution. But it's low likelihood because we have really little information about that. And so there's a number of reasons why ice modeling is challenging. It's still in its infancy. We have large-scale systems, and we have a lack of understanding of some processes. We also have a number of observations, but they're all at the surface of the ice. We have lots of observations about surface observations, depth integrated quantities, but very little information when it comes to what's happening within the ice or at the base of the ice, buried under 3 or 4 kilometers of ice. So that's the kind of things that have an impact and explain some of this uncertainty, and that's what I'm going to talk about today. So what are ice flow models? As I said, they're in their infancy. What are ice flow models? Well, we're trying to reproduce the flow of ice as we see in the dynamics of ice using numerical models, and so just regular numerical models. We've built here the ice sheet and sea level system model, ISSM at JPL, with a few colleagues, Eric and others. And so it's a finite element model. And this model needs some input parameters, the geometry of the ice, forcing conditions, external conditions, and then it produces some outputs. We can calculate the temperature, velocity, and so on. And what goes into these models are typical physical equations, energy balance, mass balance, continuity equations, and all these things that we know, as well as some parameterization of some physical processes such as friction, calving, that are not as well known, but can be included in the form of parameterizations. And then we have observations. Some of these observations are used to feed in the model, the parameters, for example, the topography and things like that. And then we can also compare outputs of our model with additional observations, surface velocity, and so on. So that's what goes in these ice flow models. And just to put things in context again, we have our ice sheets here. They're formed by the slow accumulation of snow that compacts under its own weight and starts flowing as rivers of ice. And you have ice streams. There are rivers of ice that discharge and flow faster than the surrounding ice, and so the ice sheet. And then on the side you have slower ice. And then the ice does not live isolated from the rest of the climate system. It interacts with the atmosphere above through air temperature, precipitation. It interacts with the ocean underneath and at its fronts, and as well as the solid earth underneath. And then we'll talk a lot about grounding lines, and so just a reminder that the grounding lines are the point where ice detaches from the underlying bedrock and starts floating over the ocean. Okay. And so I'm going to start, so as I said, I'm going to talk about both ice sheets, and I'm going to start talking about Antarctica, looking at some key parameters and uncertainties in the projections of the Antarctic ice sheet in the future. And we've already seen the numbers for the IPCC until 2100. This has been around for some time, so I thought I should give an update on some newer results, looking at longer timescales, looking at the next 3 centuries. So what are these results? Eric mentioned in the introduction ISMIP6. So ISMIP6 is the ice sheet model intercomparison for CMIP6. And the goal is to estimate future sea level contribution from the Greenland and Antarctic ice sheets and look at the uncertainties associated with that. And so this is a community effort that included more than 15 groups of modelers in the world. And for the first time, ISMIP6 was the first effort as part of CMIP that was one endorsed MIP and lived as part of CMIP. We've seen, as I said, we've seen the results for some numbers for 2100. So now let's look a little bit at what is this MIP6 and what we do. So the idea is to simulate ice sheet evolution. And for that, because ice sheets don't live isolated from the rest of the climate system, we need to have forcing from climate models for the atmosphere and the ocean. And so the first thing is that you have to select climate models that you want to use for forcing for your ice sheet. And so we ranked them, we looked at how well they can capture correct conditions, and selecting a number of models that we used for the forcing. And then the second thing is that we want to capture the ice atmosphere boundary condition, and so use atmospheric forcing for the surface temperature as well as surface precipitation. And for a number of reasons, we decided that even though the climate models have a relatively coarse resolution, we were going to apply the forcing as it is calculated by climate models. The second thing is a little trickier. So our second interface is the ice-ocean interface. And here at the top figure shows the reality. So we have our Antarctic ice sheet resting over some solid earth, and then you have floating ice shelves on both sides with ocean circulation happening under the ice shelf in the ice shelf cavities. But climate models look like that. They don't have ice sheets. They have just a little thin layer of ice that receives precipitation, no ice shelf cavities, no ocean conditions, and so on and so on. So the first thing you have to do when you want to look at, and so you have ocean conditions, but they're only here, far field, outside of the ice shelf cavities. So the first thing you have to do if you want to prescribe conditions at the base of the ice shelf is to extrapolate these conditions and find a way to fill in, recreate these ice shelves. And so that's the first thing to do. And then once you have ocean conditions, you can look at the melt and use parametrization to estimate melt at the base of ice shelf. So that's roughly how we go from climate conditions to forcing for the ice sheet. Now let's look at some results, but before that, as I said, there was about 16 actually modeling groups that took part in this ISMIP6 effort, and using 11 different ice flow models. And so we developed here ISSM. There are a number of other ice flow models in the world. And this is a huge table. I'm not expecting anyone to read and to remember all of that. But the idea here is that these models capture the different stress balance approximations that models are using. It captures different resolutions. Some models run at a few kilometer resolution. Some run at 30 kilometer resolution. They have different ways of capturing ice front migration and calving. They have different ways of computing melt in these ice shelf cavities and using different ice melt parametrizations. So overall, that captures the diversity in our community. And these groups submitted three sets of simulations, totaling 390 simulations. That's a lot of data to look at. So what do we do with that? So these are results similar to what we've seen before. We've just looking at 2100, and so by 2100, the Antarctic ice sheet, depending on which model and which climate forcing you use, can lose between up to 30 centimeters of sea level equivalent. And then that's what happens when you look to go to 2300, so much longer time step. And we can lose more than 4 meters of sea level equivalent from the Antarctic ice sheet. And actually, most of the simulations that we look at stop in 2100, but that's pretty much where things start to be really accelerating and you start to have a lot more sea level contribution and increase in uncertainty, and the gap between these different models widens significantly. If you look on, so we're using these 4 different climate models here. If you look on the right, that's the spread of results for each using forcing from each climate model for all the ice models that used it. And so we see that most of them have a similar range, except for the CCSM4 model that has a lot less sea level contribution. And we can also do the same thing looking at the spread of results within each ice model. So this is the spread of results for a given climate forcing, and this is the spread of results using each ice model, looking at the spread of results, applying different forcing. And we see that some ice flow models are relatively insensitive to changes, and there's a little limited variation when using these 4 different conditions, while other models have a much wider range of results, showing that some models are more or less sensitive to conditions that are applied. Okay, so this was the overall the sea level contribution. We can start digging a little bit deeper and see what's happening and what regions are impacted and where is the sea level coming from. So this figure here shows the thickness change, so the average thickness change over these almost 300-year simulations for the different models. And we see several things here. And so on the top you have the thickness change, and on the bottom row you have the standard deviation. We see that ice shelves are melting extensively already in 2100, and that continues, and that's where the largest thickness changes are happening. We see that by 2100, we have limited impact on the ice streams feeding them, but as time goes, these ice streams start to thin extensively as well. For example, here, feeding into the Rhône-Filchner ice shelf, we see that the Amundsen Sea start experiencing more thinning inland, and then as you continue to 2300, you have extensive thinning and massive changes in pretty much all of West Antarctica. East Antarctica has a few regions impacted, close to Totten ice shelf, but the changes are much slower. And if you look at the color here, this light blue color all the way to 2300, we've increased precipitation happening with warmer air conditions that can transport more moisture. And if we look at the standard deviation, we see that, well, this overall increases over time because we have a larger spread, but we can also see that the ice shelves have really limited small standard deviation because by 2300 they have pretty much melted entirely, and that some regions feeding them have already also small standard deviations, while other places like the Amundsen Sea have this really large standard deviation with really different changes between the models. So what's happening here? We can also look at how the grounding line is retreating during this period. And so on the top, we have all of Antarctica, but then most things are happening in West Antarctica. So zooming on the West Antarctic ice sheet, we can see, again, for these 3 times, 21, 22, and 2300, the percentage of the ensemble that has grounding line retreat. What does that mean? So initially, the grounding lines are all situated here at the transition between this floating ice shelf in dull blue and grounded ice. And then, as in our ensemble, some models have their grounding line retreated over time. And so the colors show the percentage of the ensemble that has its grounding line retreated by 21, 22, and 2300, with dark red colors showing an agreement between all the models where grounding lines have retreated, and then in blue, only a small percentage of the model retreating. And so we see that, well, there are a number of results, but we see that by 2300, there's a strong agreement between the models that this region here, Bergenstock ice, close to the Bergenstock ice rise, has retreated for all of our models. Similarly, the Sipol Coast has experienced retreat from all the models, at least to some extent, and then the extent of the retreat varies slightly between the models. On the other hand, we see that the Amundsen Sea region, which is this region where all these changes are happening already, has a strong disagreement between the models. We've only some of them simulating a complete collapse, pretty much, of the Amundsen Sea regions, while others have their grounding line and stuck here at where it's currently located. So now let's look a little deeper into that. And we're going to look at the grounding line retreat over time for these three lines here on Thwaites Glacier, the Sipol Coast, and Bergenstock ice time to see how these large retreats are happening, when and how they are happening, and comparing them between models. So we're going to build this figure. It's a little weird of a figure, so we're going to build it step by step. So here we have this line from Thwaites Glacier, and so we have here in brown the grounding line, the bedrock topography at the base of the ice in brown, and so this is the present-day grounding line, and we're moving further inland. And then we have this spread here of bedrock topography used by the different models, and there's pretty much one data set that exists, so the differences come from interpolation and resolution, but they're all using the same data set. And so on top of that, we're going to add the grounding line position over time. So we have our time here from the beginning of our experiments in 2015 all the way to 2300. And so if we add the grounding line position from one model, this is what it would look like. Grounding line starts here, and then over time stays here, doesn't change much, and then starts retreating inland towards the end. And so these vertical lines show no grounding line change, while on the other hand, if you had an unstoppable, very rapid retreat, you would have some horizontal lines. So this is for one model. If we add all the models that we have, it looks something like that. And so again, remember, this is the Amundsen Sea sector, where we have kind of half of the models have their grounding line stuck where it is today, and not changing. And the other half have their grounding lines retreating. And the time at which it starts retreating varies between the models. But then if you look at the slope, they're all pretty much the same. They're parallel. That means that the retreat rate at which all these models simulate the retreat rate is the same between the model. But they start at different times. That means that the forcing and the external conditions are changing. And so this large retreat here is dictated not by the external conditions, but almost entirely by the topography and therefore the shape of the bed. So this is for Thwaites Glacier. If we look at these other two regions, the picture is the same with parallel lines, and then the retreat stops here on this prograde bed, and pretty much all models have their grounding line that rests on this region here, and same for the Sipol Coast, with most models having parallel line. What does that mean? That means that all these retreats are controlled by the topography. And while we've been surveying the bed for the last 3 or 4 decades, we still have huge regions, especially inland, where we have very little information. And therefore, these models agree because they all use the same model, but there's large uncertainty in there. And therefore, we need to continue mapping bed if we want to be able to capture that. Because agreement does not mean that we know what's happening. It means everybody's using the same data set, and therefore that's controlling the large retreats. Okay. Another thing that's been a huge discussion in the ice modeling community in the last decade or so is the impact of ice shelf collapse. We've seen the collapse of regions like Larsen B, and models have been trying to look at the impact of that on simulations. And so here, we can estimate ice shelf collapse for these 4 climate model conditions. And the collapse is based on, we know that Larsen B collapsed after experiencing extensive liquid water at its surface. And so we can calculate the amount of liquid surface at the surface simulated by these climate models, and based on that, simulate collapse in the model. And so these 4 models simulate vastly different ways of collapsing. We have the time scale here. This AHAD-GM has pretty much no collapse. CESM4 has ice shelf collapse happening from the front and then retreating inland, while CSM2 and UKSM have a large amount of liquid water at the break-in slope from the ice going from the interior and then becoming more flat on the ice shelves with Carpatic winds and foehn winds. And so if you look at that, we actually probably created the largest icebergs you can think of as this whole area is becoming detached. So what's the impact when you include this collapse? This is the picture we've seen before in the absence of ice shelf collapse, and we had up to 4 meters of sea level rise. And this is new results, including the collapse, and we have up to more than 6 meters of sea level contribution in the most extreme cases. And on average, there's an additional 1.1 meters of additional sea level when you include this collapse by 2300. Yeah, we can do questions now, sure.
Now, okay, so I didn't fully understand. Did you describe the ice shelf collapse, right?
Yes. So the question from Surendra was, the question from Surendra is like, how is this collapse happening? So we can estimate from climate models ice shelf regions that are unsustainable and cannot sustain ice shelf conditions based on this amount of liquid water. And then when that happens, models retreat their front and prescribe ice front retreat following these conditions. So it's the same between all the models, so we can look at the impact. Okay, so we have an additional 1 meters on average, and we can see that now this shows the percentage of the ensemble mobbers that ungrad, same as what we had before. And on the bottom graph, we see the percentage difference between what we had before and what we have now. And so we see the retreat is more extended, not so much for the Verney-Filchner ice shelf, but a lot for the Ross ice shelf, as well as for the Amundsen Sea, where we have now a much better consensus on terms of retreat and timeline of retreat in this region. One more thing about these results, I wanted to look a little bit about uncertainties, because we have different climate models, we have different ice flow models, we have the presence or absence of collapse, and how are these different sources of uncertainty playing a role in these results? And so for that, we use multivariance analysis to look at the impact, looking at the results from our ensemble, looking at the role of ice, climate, and collapse in the uncertainty. And so here we have the uncertainty from this ensemble, and so black line shows the total uncertainty. And then the uncertainty in blue is the largest, and that comes from the choice of ice flow model. And so that remains the dominant source of uncertainty over the entire simulation period, while the other ones are kind of clustered together. We can also look at that in terms of the percentage of the variance that is explained by these different sources of uncertainty. And something that surprised me is that, so over the 21st century, we see that the role of the climate, the choice of climate conditions from these different global climate models is increasing until 2100. And it was kind of expected that this would continue over time, but we see that after that, the role of climate kind of remains the same. And this is prefacing that this is all using high forcing emission scenarios, so all RCP 8.5 or equivalent. But the role of climate is remaining the same. Collapse also plays an important role. Up to 10 to 15% of the uncertainty is explained by the presence or absence of collapse. There's not much happening until 2100, but that grows quickly after that. But then over the entire period, more than half of the uncertainty is explained by the choice of ice flow models. And so that remains the leading source of uncertainty in these projections. Okay, so we saw that ice models continue to remain the dominant source of uncertainty in these projections. Why is that, and what can we do about it? So these, using the same results, we can compare how models simulate the recent evolution of these ice sheets with observations. And we have, IMBY is an intercomparison exercise combining different sources of observation from GRACE, but also altimetry and other methods to create observed mass loss from the Antarctic ice sheet and the Greenland ice sheet. So in blue here, with the standard deviate 2 sigma uncertainty around that. And then in gray, you have all these lines I was showing before, and so that's for the 2000 to 2015 period, all these lines I was showing before from the different ice flow models. And so not only are they not within an uncertainty, they have a wide range, For Antarctica, some over-predict mass loss, while some under-predict it. But if you look at Greenland, it's almost even worse because all the models underestimate the mass loss over the past 15 years or 20 years. And then that probably means that our projections underestimate changes. So why is that, and what can we do about it? So remember, we have here our ice flow model, and as I said, we have some observations that we can use to calibrate and validate these models. And so what people have been doing and so in there, we have, backwards, and we have some, no, it's not showing, that's fine. And so, for example, if we zoom in on the momentum balance equations, which is what you use to simulate ice velocity, and we have observations of that, these are your momentum balance equations. And so just Stokes flow, that might sound familiar. And we know many things, but there are some things we don't know. Again, we have observations of the surface of the ice, but we don't know much about what's happening at the base of the ice, buried under 3 kilometers of ice. So the basal friction here, friction coefficient, is unknown. And so if you want to, but that's needed, and that's part of your equation, that's your boundary condition, so it's needed. What do you do about that? Well, you can try to infer it, because we have surface observations that we're not really using in our model. So we want to, the direct problem is, for a given friction condition, friction field, you can calculate the ice velocity. But we want to do the opposite. We want to do the inverse problem. We have observations of surface velocity, and we want to find what's the friction coefficient that is causing these surface velocity. And so, unfortunately, this is a much harder problem to solve. And so, to do that, we can do variational data assimilation and constrain our functions. And so, we have our cost function, and we want to minimize the distance between the modeled here Vx, Vy, and the observed surface velocity at the top of the ice. So we have these observations, and we have our model, and we want to minimize that. But we also want to make sure that we still fulfill all our equations and conditions. And then here in red leaves our basal friction that we don't know. And so in order to do this variational data assimilation problem, we calculate the derivative of this cost function with respect to this unknown parameter alpha. And then once we have the gradient, we can use a joint-based gradient and steepen descent algorithm and things like that to infer the friction. So what does it look like? We start from an initial guess. Well, let's say we don't know anything. We use a constant friction everywhere. We model the velocity associated to this field, and then we look at the difference. We calculate the cost function, the difference between the model value and the observation. We calculate we have our cost function, we calculate its derivative with respect to the friction coefficient, and then we can iterate and update the basal friction. So we have a new estimate, we recompute the velocity, and we keep iterating until we have a result that's close enough to our observations, and we're happy with the results and match more or less the velocity. So that's what people have been doing for a while. That's how ice flow models are initialized. And so for the longest time, we had very few observations. The first velocity map of Antarctica is from 2011, just a few years earlier for Greenland. And so, but if we look at what we're doing, so we do this data assimilation. We have one observation here, and this is time. Let's say this dotted line is the truth, and we have our observation here. And we want to do this optimization problem and have our model capture these conditions here at this given time. We initialize it here, and then we hope that as we start running our transient model and simulate its evolution over time, we will more or less capture changes that are happening. The truth is that, well, it's easy to fit something through one point, and when we run our models, it will just go this way or that way or anyway. And so we really don't capture well the evolution of changes. But over the past decade, the number and quality of remote sensing observations, including surface velocity, has increased dramatically. And so now, instead of having just one point, we have a collection of points. And so it would be good to use all these different observations to constrain our model better. And so if we can, our optimization problem is changing from just like the integral and minimizing that just at a given time over the entire domain to having these number of observations at different times. And so we're summing that over these different time steps, the difference between the model and the observations. And so hopefully if we do that, we can capture better the changes over this period over which we're going to constrain, and then the model will capture better things in general. So, and this is kind of similar to what people here are doing with ECHO, trying to assimilate as many observations as possible and create an ocean state estimate. Ice models are like much younger and kind of in their infancy, so it's just kind of lagging behind and trying to catch up with things that are done in other disciplines. So this is an example of doing that on Kjær Glacier in West Greenland. So Kjær Glacier is here, and it's a glacier that has really good observations over the past 30 years, actually, starting in 1985. And so we want, and so that's figure shows the velocity of Kjær Glacier in 2007 and its ice front position. And so this glacier retreated. It has like kind of two separated fronts here and there, and the front retreated between 1985 until 2015. And so we do exactly what I just explained, infer not just the friction, but also try to infer the rheology, and we have more constraints using automatic differentiation. And so we want to do that over like 2 decades. We have 3 decades of observations. So we did that over the first 2 decades, and then compare the results when we run the model forward after that. And so compare the results over the 2007 to 2019 period. So this is what we were doing before. We capture the conditions and with what we call snapshot inversion. So we have this just one data set in 2007, captured the condition here, and so you match well the velocity. And I forgot to mention that these colors show here different points along this flow line here in the middle of the center line of the glacier. And so these triangles show the observed acceleration of the glacier. We initialized it in 2007, and the solid line shows the model response. And so the model underestimates the acceleration of the glacier and therefore underestimates the mass loss and the discharge, exactly what we've seen in these global projections. Instead, here, we can calibrate the model over these more than 20-year period for which we have observations. And so we have annual velocity observations, and we constrain the model over this period. And you will notice here that over this period, not that much is happening. The glacier is accelerating a little bit, but not that much. And then in 2007, we let the model run over time, prescribe its front still, same as we were doing here, but we let the model run, and we see that the model captures much better the acceleration over its flow line close to the front, as well as all the way inland, even though our calibration period not much happened during this period. And then we can compare the mass loss just for that glacier with independent observations of mass loss. And we see here in black we have the observation of mass loss, and then we have in blue the snapshot inversion, and then in red the transient inversion, and the results are really close. I don't think we see well the uncertainty around that, but that's fine. You get the idea. We capture a lot better the mass loss from that glacier. So we've an independent observation. So that's great, and we were able to calibrate them all over a 20-year period. Does that matter? What happens if you have this glacier? For this glacier, we have really good observations, but not all glaciers are like that. So what happens if you only have like 5, 10, or 15 years of observation to constrain your model? So here we compared the results with using 15, 10, and 5 years of observations to see how that impacted the results. And so even in the case where we only have 5 years of observation to constrain the model, once we let the model run, it captures the acceleration a lot better, even though we had a shorter period of data assimilation. And so that's what, and comparing again with these independent mass loss, the results are not as good. The longer calibration period provides better results, but we still have a strong, much better agreement than when we were doing just these snapshot inversions at a given time. And so all these runs were done with prescribing the ice front position in our model. Can we also use similar techniques to calibrate other parameters in the different processes that we don't understand as well? For example, this is how we typically simulate calving in this model. It's like a function of ice velocity, and then you have this threshold, the stress of the ice, and then this threshold which tells you when you start calving. And sigma max here, we have no idea what this is. So can we do similar things to calibrate that? So to calibrate these unknown parameters. So same thing here, we have our cost function, but this time we want to look at the difference between the observed and the modeled ice front position. So your cost function is the difference between these positions. And turns out you can actually do that as well. And if you do that, you can simulate the ice front position that has a decent agreement with the observations. It's not perfect, but at least you can calibrate that together. So all these results were done by postdoc Youngmin Choi, who was a postdoc here, except he was here during COVID, so maybe not many of you might not have interacted that much with him. That's unfortunately. And that's great. But this is just one glacier in Greenland. And Greenland has more than 200 glaciers. So how do we move forward to doing large-scale assimilation? So this is the work that Jessica Badgley, a postdoc at Dartmouth, has been working on over the past year or so, trying to expand that to larger regions. And so we're looking here at northwest Greenland here, so these two regions, central and northwest Greenland. And we're able to continue having simulating glaciers at really high resolution, up to 400, using a resolution of 400 meters in the ice front, because these are narrow fjords and glaciers that you have to capture accurately. And so we're changing things slightly here. All these glaciers don't have such good observations over a long period, and so we're focusing on a much shorter period from 2007 to 2022. And these so here we have observations of how Greenland is changing, and as we've seen in the race observations, Greenland has a really strong seasonal signal. So that's something really important. And so if first, let's build things step by step. So first we can start by using snapshot inversions as is typically done and see what happens if we model this region at high resolution. So here we have our observations with uncertainty in black and gray, and then we have our modeled mass loss from that region. So there's some discrepancy even with that. Then one thing is that we were using annual ice front position and annual velocities for here glacier, but a few of these glaciers here have really strong seasonal changes in ice front position. So what happens if you start by adding seasonal processes? And so this is the velocity that you obtain for these glaciers. We've just used snapshot inversion, using a fixed ice front and retreating it just like using annual values. You can then, but these glaciers, as I said, have strong seasonal changes. This is Jakobshavn-Isbrae, and just zooming on, so results compilation of front positions by Chad. And then we can look at the seasonal changes from that, and we see that we have very strong seasonal changes, with the most advanced in April and most retreated in August or something like that. And so we start by adding these seasonal front positions and seeing what's the impact. So if we look at the results here, we go from these changes, these velocity, to these kind of velocity, where we can see. So we have two different glaciers, Jakobshavn-Isbrae here. This glacier has really strong seasonal changes, and this is velocity over time. So we can capture seasonal changes by just prescribing the ice front position. This glacier is mostly driven by front conditions, and so that's why we can capture that. For this other glacier, Upper Navik, slightly north, even though we include seasonal ice front positions, this glacier does not have such large seasonal changes in its front position. It's not really driven by front conditions, and so even though we do that, that doesn't really have much impact. But when we do that and we add these seasonal changes and start to add seasonal processes, we see that we have 6% more sea level contribution from this entire region, and we start to get closer to the results that are observed from these other data sets. The next thing, as I said, is that we want to use transient assimilation to calibrate that better. And so since 2007, we've had a lot of observations, so way more than annual values. We have seasonal and almost monthly values. And so here, using a compilation of both optical and INSAR data, we want to calibrate this region and all the glaciers in that region with all these observations. And so when we do that, these were the previous results in purple, and then we start adding these new data sets and calibrate them all over this entire period, and now we can we can capture better the overall change and the mean velocity of both glaciers. And I don't know why the glaciers, yeah, oh no, that's something else. And so of both glaciers, we capture better the signal. It's not perfect, but we start to add more and more processes to capture these changes better. And when we do that, we have another 12% of sea level contribution from this region. And we start to see that these yellow lines starts to be within the uncertainty of our observation. So we are able to capture things and are able to get within the uncertainty of these mass loss estimates. To finish this up and try to just go back where we started, what's the impact of these things on our projections? So we have this small assimilation period, and you can kind of see the black line here over which we had constrained our model. And then we can run simulations of that regions until 2100, both for the snapshot inversion in dashed lines, in purple, and with the transient assimilation in yellow. And we can compare the impact of using this different calibration method and initialization of our ice model with using different climate conditions. And so here we have two scenarios, RCP 8.5 and 2.6, in the with the dashed lines and the solid lines. And these are the results showing these four different results. And we can see that over the first 30 years, the calibration method matters most. And so the result is, if we're interested in short-term projection, decadal timescale projections, the way the model is initialized has a much bigger impact than the climate scenario and the forcing that we're using. And after about 30 years, the calibration and climate conditions matter almost equally. And then after that, the climate scenario starts to have a bigger impact than the calibration method, but the calibration method continues to have about a 15% impact in terms of like the mass loss from that region. And so that shows that as we continue to improve the model and capture these conditions better, having good observations to calibrate the models is critical. So I think it's about time to stop, so I'm going to stop here with some conclusions. First, we've looked at this large ensemble of simulations from the Antarctic ice sheet, and we saw that the bedrock topography was key in driving the retreat of many areas in Antarctica. And so, therefore, having good observations of ice topography, which is extremely challenging, is going to be critical if we want to look at these long-term projections. We also saw that currently the models have a hard time capturing the mass trend. And that's not just one, it's like all of the models. But we can start to do better by using the observations that have been captured and measured over the past decade or so. We now have access to great number and quality of remote sensing observations that we need to use better in our models. And so there's some efforts towards that. We're far from having a comprehensive and large-scale assimilation techniques, but we're working towards that. And that allows, even when we have observations in periods that capture limited changes, that allows to improve projections in large changes beyond that. And we see that as we are moving towards more and more refined projections, we need to have high temporal and spatial observations if we want to further constrain the models, validate different processes such as calving, friction, and things like that, if we want to improve these projections both on short timescales and long timescales. I'm going to stop here. Thanks a lot for coming here. Thanks for inviting me, and I'm happy to answer questions.
I got a question. Seems like the 4D-VAR temporal approaches here work well for specific glaciers. I mean, some of the matches you saw, that you showed there were incredible. Some other glaciers clearly don't care at all, right? And I think at JPL would be interested to know, we're having missions right now that are going to fly like pre-fire, for example, that could improve our knowledge of a lot of the atmospheric forcings. I think it would be interesting to know how much you think of Greenland is potentially improvable by improving the atmospheric forcings and how much of it will just not respond at all to it and will be more driven by maybe our knowledge of the bedrock and the calving front dynamics, things that are essentially very solid earthy or fracture related, mechanical.
So one main difference, so I guess you're referring to something like this, and so one thing is that there are glaciers are the main behavior is driven by different processes, and so here these results here are for Yakam 7 Isbury, which has extreme seasonal advance and retreats of its front position. So if we can capture that well, we can reproduce a number of changes. Other glaciers, as you said, atmospheric conditions also have an impact, but that's more for the mass loss. And so that's something that we would see in more like if you look at the mass loss, we would capturing this better will help with that. The problem is that a number of glaciers in Greenland are driven also by hydrologic conditions. And so this glacier here, no matter what you do with the font, it's not really capturing that, because one other thing that matters a lot is that you have seasonal changes in water pressure at the base of the ice, and sliding will evolve tremendously because of that. And so these changes are mostly driven by hydrologic conditions. This is something I didn't present because it's too much in progress and we don't have some conclusions, but the next thing is to try to constrain basal conditions and friction, not just, because in all these simulations I've shown, the friction is calibrated to best fit the entire time series and it's not changing over time. But we know that for these glaciers that's wrong, that's wrong for sure, and it has an impact. So we need to move towards asymmetric friction over time, and using some kind of seasonal cycle. For example, we know there's more sliding in summer and less in winter, and we can calibrate that so we can capture these changes. And we have no idea what's happening at the base of the ice. Again, like basal hydrology is like one of the hardest things to do because we have absolutely no observations, very little things we know. But maybe now that we have more observations, and we really need very high temporal observations, because we need in these runs we use monthly or as many velocity as we can, but you need at least monthly, if not like weekly or something like that, capture velocity at weekly time steps if you want to really see how the changes are happening on small time scales to constrain the basal condition, the hydrology, and combine that with precipitation, the role of liquid water, the presence and extent of liquid water that will percolate through the ice, go to the bed. And then by combining things, maybe you can be able to say something about how subglacial hydrology is happening, what's happening, how it's impacting the friction and the base and the effective pressure at the base of the ice, and then start to reconstruct things at the base of the ice on a more like seasonal time scale. So I think it's atmosphere plays a role, but it's also the subglacial conditions that have a really strong impact in that case. And for that, if we want to constrain that, we need extremely high temporal resolution observations of things like fonts and velocity and altimetry and things like that, so we can constrain on smaller, a lot more accurately on over small periods.
Hi, this is Sun from the web. I'm from the atmospheric physics and weather group. One curiosity is why there is one place that you have strong seasonal cycle and there is one place you don't have. Is that what's the mechanism called that caused that difference? Yeah,
that's a great question. There are several things that come into play in that. First of all, some of them are caused by the extent of the ice front, and for some glaciers, the ice front retreats and advances seasonally over just a few hundreds of meters, while for others it's much larger, and you have much stronger advance and retreat, and so that's one of the reasons. Another reason is that, for example, Yakam 7 is not very sensitive to hydrology conditions because it's such a fast and thick glacier that there is always a lot of water at its base. It's flowing so fast and you have so much frictional heat that even in winter you create enough water at its base to lubricate the bed and flow faster. While other glaciers further in the north or that not flow as fast don't have as much basal friction, and therefore the input of liquid water in the spring and in summer that goes to the bed will lubricate the bed and create wet conditions at the base which are not present in winter. And therefore you're going to have like alternating conditions in winter and summer with presence or absence of water at their base. And so it really depends on the glaciers, and so typically the bigger ones, faster ones will have more frictional heat and therefore have presence of water over the entire year or close to that.
Oh, okay, thank you.
Sure.
In the room.
Hello, Ellen. Can you hear me?
Yes, I do.
Right, hi, my name is Mark Richardson. I'm with Atmospheric Science People as well. I asked about the spin-up of the models in the ice sheet MIP. Apologies if you covered it, but I know that ocean heat content can end up with drifts if you fork off the run from the control at the wrong time. Can you comment on whether this matters for the ice sheet runs and if you have accounted for it somehow?
Sure, absolutely. That's a great question. So what are the drifts? So the problem is that, so some ice models are initialized, as I said, over the very recent period, starting from just 2007 or something like that. Other models do long spin-up over glacial times, over thousands of years, and end up in more or less steady-state conditions as of today. And have smaller drifts. And so what you see, if we go back here, comparing models and observations here, if you look at that, these are pretty much the drift that you have in the models. And so some models, if you look at Greenland, are of like limited changes, and that tend to be the models that are initialized over long periods, while models initialized in 2007 or close to that have bigger drifts. Sometimes if you look at Antarctica, growing mass instead of shrinking it and things like that. The problem is that ice responds on a really long time scale. So unlike what you might be able to do for the atmosphere, I don't really know how the atmosphere works, so don't take this with a grain of salt. But even if you do some spin up or try to run for a little bit of time, your conditions, the drift continues on for centuries and millennia. And so that's why some models run for thousands of years before. But then you end up with conditions that are far from what you have today. So typically an ice sheet that's much thicker, much bigger, and contains more ice, or much thinner and has a lot less ice than you have today. So you have a better trend, but you start with conditions that so how much do you trust? So that's that you have to correct for that. So that's why there are these two approaches. None is perfect, and that's why by trying to initialize over like the remote sensing period, for example, as we're trying to do over the past decade or a couple of decades, we hope to capture the trend better. And then when you run from that, we have a much better match with observations, and that's kind of what we're doing when we're looking at the model over like 2 decades, and then we let the model run based on observed reanalysis for atmosphere and other conditions, and that captures the acceleration much better. So by capturing changes over a decade or a couple of decades, we hope to, that's what we're doing, and we capture better these changes, and then projections should be more reliable. This is, again, not of all of Greenland. We have a lot of work ahead to extend that to the entire continent. Antarctica is even bigger. It's going to be another challenge, but I think this is one good approach to capture these changes better and improve our projections.
So we have one question
Thank
in the
you.
room. We just have a minute here left. Do you want to?
Thanks. Very educational for me. And I think you partially addressed this question maybe, but so I wanted to pinpoint on the surface hydrology and generation of or meltwater on the surface, and how important is that in calibration of these long-term models?
So you're asking about the role of water and the surface and that. So the surface, the climate models capture precipitation in the various forms, solid precipitation, evaporation, and liquid precipitation. And so that's what is applied at the surface. But currently, the models don't really use liquid precipitation, so because that can warm up the entire ice column, go to the base, and this is not really used. This is a process that's not really well captured by models currently.
And how about like meltwater generation into snow, like melting snow and that effect? So you are saying that's not captured too much?
So this is not really used in the models.
So would it have an impact if it were, or is it just because it's not?
There are several things on which it's going to have an impact. The first one is that if you start to have more liquid water will percolate through the snow and fern and will warm it up, and so that will facilitate ice deformation, and you can flow faster if you, or like ice is a viscous fluid, so same as honey, it's warmer, it's going to deform more and flow faster. So that's one process. Another thing is that as you start to have a lot of surface water, it's not going to stay at the surface. It's going to go through whatever is not going to refreeze within the snow and fern will go probably all the way to the base of the ice, and then you will have more water at the base and start to flow faster. And we go back to the things we just discussed. And so as the climate warms and the extent of the liquid water progresses inland, you're going to start impacting larger and larger regions, and so that's going to change. Another thing where it matters is for ice shelves, because ice shelves are unlike the grounded ice, where the water will just flow through the base and just gets evacuated at the base. On ice shelves, that can cause like collapse of ice shelves, and therefore that's what we talked about briefly about ice shelf collapse. If you have too much liquid water, the ice shelves are not sustainable anymore, and they can collapse. And so knowing how much and where there is water matters a lot, especially for these ice shelves.
Thanks. Do we have any more questions in the room? Or Jorge, did you want to ask your question, or shall I ask for you? Jorge.
Oh, thank you. Thank you, Margaret. Yeah, I'll go ahead. From the remote sensing perspective, how important, one of the issues with remote sensing products is obviously the quality in the Arctic and the Antarctic. Looking at sea surface temperature from the air-sea coupling, obviously, and also the impacts on the ice melt, how important do you think accurate sea surface temperatures are, in the Arctic, for example, and the Antarctic also?
So yeah, you're right. That's a great question. The accuracy obviously matters. I used to not think much about the accuracy because the models were so off that we were like way beyond the uncertainty in the observations. But now we're moving towards that. So that's something we have to think more about to make sure we don't overfit our observations. And I didn't talk much about that, but ensuring we don't overfit these data sets. In terms of sea surface temperature, I think it's a little outside of what I know, and so other oceanographers might be able to answer that better. But this is key to capture ocean conditions close to the ice, and so that's where it's going to matter a lot, so we can have accurate conditions close to the ice, because that drives most of the changes that we've seen, both retreat of glaciers in Greenland melting at the front, that starts the retreat of these glaciers, as well as thinning ice shelves in Antarctica. It's not at the surface, but the conditions will matter as well. But I'll refer to oceanographers for a more in-depth answer of that question.
Well, I think we're over time, so we'll thank Helene once again. Thanks so much, Helene.
Thank you. Thanks a lot. Great to be here, and thanks for inviting me.